This video is going to show how we use both left and right Riemann sums to approximate integrals of functions, and in this case it'll be for a function that's defined by a table of values. So over the interval from 0 to 10 we know 5 values on this function, and those values are given to us in this table. The problem says to use a left Riemann sum with 4 subintervals to approximate the integral from 0 to 10 of f of x dx. And in some problems they won't tell us how many intervals to use. Instead they'll say use a left Riemann sum with a number of intervals defined by the table or suggested by the table. And in that case it's useful just to help ourselves see what's happening if we look at the changes in the x values. We go from 0 to 2, from 2 to 5, from 5 to 9, and from 9 to 10. So this table indicates that we should use 4 subintervals, even if we're not told that explicitly. Because we know that the integral from 0 to 10 of this function is the same as the area under that function's curve, it's useful for us to look at a graph of what we do know about the function. So we can plot the points that were given. On the graph we have a point at 0, 3, at 2, 1, at 5, -1, at 9, 2, and 10, 3. And we can start to visualize our Riemann sum because we know that we're going to be making rectangles to approximate the area that's under this curve that we don't really even know where the curve is going. Because it's a left Riemann sum, the height of each of the rectangles that we make is going to be based off the outputs at the left side of the interval. So we have a height of 3 over our first interval that has a width of 2, a height of 1 over our second interval that has a width of 3, a height of -1 over our third interval that has a width of 4, and a height of 2 over our final interval that has a width of 1. And the areas in these rectangles that are above the x-axis are positive areas, and we'll change color to red to show that the area that's below the x-axis is going to be a negative area. Now let's write out a formula for our left Riemann sub with 4 subintervals. I'm going to say the integral from 0 to 10 of f of x dx is approximately equal to f of x1 star times delta x1. And remember that x1 star just means that we're allowed to choose any x value in our interval, in our first interval, to be x1 star, and we've chosen to make it the left endpoint. But I like to use this notation here because it allows us to have the same subscript numbers in both of our parts of this first term, and for each term they'll match up. And I think that works out well for us to help us understand what we're doing. So that takes care of the first rectangle, and then we're going to make a second rectangle for our second interval. That's going to be f of x2 star, the output, somewhere on the second interval, multiplied by delta x2, the width of the second interval. We'll keep on going. F of x3 star delta x3 plus f of x4 star delta x4. Then we're ready to plug the values that we know into this formula. So we're saying that the integral from 0 to 10 is approximately equal to 3 times 2 plus 1 times 3 plus negative 1 times 4 plus 2 times 1. And we're just going to simplify this. We have 6 plus 3 minus 4 plus 2 is equal to 7. So the left Riemann sum approximation for the integral from 0 to 10 of f of x dx is 7. I'm going to scroll down a little bit now so we can see our second problem. I will try to keep the table up there at the top of the screen so we can refer back to it. Second problem says use a right Riemann sum to approximate the average value of f of x over the interval from 0 to 10. That means we're going to have to remember our average value of a function formula. We know that f average is equal to 1 over b minus a, the length of the interval, multiplied by the integral from a to b of f of x dx. And in the case of our function that's defined over the interval from 0 to 10, we get 1 over 10 times the integral from 0 to 10 of f of x dx, which we'll need to approximate by a right Riemann sum. So this is going to be approximately equal to 1/10 times 1 times 2 plus negative 1 times 3 plus 2 times 4 plus 3 times 1. Now let's make sure we understand where those values are coming from. We really are still using this same formula for the Riemann sum, only in our x1 stars, really all of our xk stars we call them, we've chosen to take our outputs from the other side of the interval. So instead of making x1 star the value here at x equals 0, we're changing that to make x1 star the output where x is equal to 2. And that really is going to change the shape of the area that we're finding. I'm going to see if I can get this to come on in my yellow highlighting. So we have that area over the first interval, and the second interval drops down here to a height of -1. And then we have the area up here, and finish with the area up there. So in this function, it makes a pretty big difference which endpoints we use, whether we use a left Riemann sum or a right Riemann sum. But let's go ahead and get back to our problem, finish finding this average value. So this is equal to 1/10 times 2 minus 3 plus 8 plus 3, which works out pretty nicely. In this problem, we end up with 10 over 10 equals 1. So according to the right Riemann sum approximation, the average value of the function over the interval from 0 to 10 is 1.